Good afternoon, everyone. Welcome to IME 765. Today is April the 22nd. In the beginning, again, let me stop the video and share the window, my screen with you. Okay, so can everybody see my screen here? Hello,
yes,
Arab.
Yes.
Okay.
Yeah. Sorry for.
That's okay. It's okay. So in the last class, we've introduced the linear regression with multiple outputs. Remember? Okay. So we've introduced the case for. Let me start my annotate here. My annotate. Spotlight. Go this way. That's gonna be more. It's gonna be easier, I think. Okay. So we've introduced the normal equations and OLS solution, which is actually here. No, sorry. The OL solution is not here. The OL solution is right here, which is this solution. Okay, and we've discussed the idea why this one works. Okay, the proof is right here, super simple. And also we've mentioned the case that if I do want to add a weight, be careful that in real application for multiple, this kind of multiple output regression, the weight is very, very popular. It's very, very rare that you can see, for example, you have multiple outputs and you don't have a weight. It's very, very rare. And unfortunately, in what's the name of the book? Elements of Statistical Learning, I call it ESL. In that book, it didn't include this part. This part was included by myself. In real application, for example, if you want to, fit something and with several different outputs, you probably will consider it. So in this case, to let you know that what you're going to do is you're just going to consider each x to be a x times square root of w. Okay, matrix. Okay, all of them are matrix. So remember, in the end of the last class, I showed you how to get this formula directly without using the derivative something. Remember, you just consider the x and also the y as the thing with a multiplication of w a half. Okay, again, it's a matrix a half. And then you plug in everything there, you're gonna see this part. Okay, so today we're gonna introduce the application of such multiple output linear regressions for categorical outputs. So for the categorical output, one important thing is that it's just a category. Without a loss of generality, we define it this way. We model the problem with m outputs, yi to yn, and yk equal to 1 if the label of the data is a really k, and all other yks are 0. And of course, the summation of y1, y2 till 1m should be 1, indicating that it must be one label must be the category of the data x. Okay, and first of all, using the conclusion that we got here, so this still works because categorical output is one application of these multiple outputs. Okay, so this should still be working. And then the thing is, that let me see where I can make it to that way. Let me see. Okay, here we go. So then the thing is that I'm gonna use a vector function, call it f hat xt. So make this one to be the prediction. Okay, it's just something like, remember, in the single level, is this lecture number 9 or 11 or 10? Let me see. This is lecture 9. In the beginning, for example, we make the y hat for each data. We have the y hat. Remember it. So here, it's something very similar. That if I have a f hat x and a vector, so this means that for a given data xt, I'm gonna use this B matrix to fit it. And this is the what? This is the estimated value, okay? Then how would you classify it? I'm gonna predict the label by what? By this way. In other words, I have so many, for F1 to Fk. I'm gonna see which fkx gives me the maximum value, and then I'm gonna predict my label to this, my x to this label. Recall that we've actually applied this idea before. In many cases, remember, in LDA, in logistic regression, we all used this idea. Remember it? And this, intuitively really makes sense, because you can simply use, for example, ideas of Bayesian, and we've showed that, for example, for what's the name, multinomial, or this kind of, let's say, multinomial distribution, and this is indeed the what? The MLE, maximum likelihood estimation. Remember, we've proven it. And I think I hope you remember it even more, because it is a problem of midterm exam. and then what we are gonna have is, can we prove this conclusion in general in a more formal way? In other words, I'm asking, hey, I'm using this way, but how do you know that this is really, correct? Is there a very clear, very rigorous mathematical proof, rather than this kind of simply this kind of analysis? And the answer is yes, we do have it. And first of all, do you have any questions in 55 and 56? By the way, in the lecture, after lecture, including and after lecture 9, I'm gonna mostly use the, put the label after the equation, even if the equation is not, later equation referred. The main reason, because in this case, if you have any questions, that's gonna be easier. Otherwise, suppose there's no label here, it's difficult, Any questions?
So, I have a question.
Yes.
In 55, we have f hat x transpose. What is f hat kx?
F hat kx means the kth element of this.
Oh, okay.
So, okay, let me open a Word, so it's gonna be easier. I wish I have a whiteboard. Really makes life much easier. But for a whiteboard, a bad point is that I cannot copy and paste. Let me see. Word document. Okay, and then let me see. It's here. Put a word here. So what I mean is this way. I have. Wait, where it is? Let me see. Okay, here 55, right? So what I have is this. I will have hat fx. This equals, let me make everything to be bold, because this vector, x is also vector, okay? This simply equals, this is actually a vector. It's a vector function. This equals hat f1, oops, take this one out. f1 is here. f1x So here you go. This fx is in this way, okay? This is this. And the reason I write it as a t, because if I write it this way, xt beta hat, b hat, that's a row vector. So I want to make it to be a row vector. That's why I make a t here, okay? So 50, this is 55. 56 tells you that, hey, because finally you're going to make a prediction, right? Because here we're talking about linear regression of categorical outputs. So how would you predict? In other words, I'm asking, hey, I'll give you an x. Which label would you predict? It's just, remember, we have done a lot of this kind of problems before in classification, right? So this tells me that I'm going to use the biggest f. There's no absolute value. Be very careful. There's no absolute value, but the largest f hat k. Put this k to predict. Use this. We're going to predict the label of x using this k. The one gives the maximum f hat x. Okay, and then first of all, is this point clear?
Yeah.
Any questions?
Dr. Shu?
Yes.
fx hat should be, maybe negative, right?
Yeah, can be negative, but
But yeah, suppose it's the absolute value of -1 is
no,
more than absolute
there's
value
no
of
absolute
positive.
value. I know this is going to be a good question. And remember, we actually discussed it in where? Remember? In one place we discussed it. It's right here. Let me see. Where's my document? Here in the SVM. Let me see where it is. I remember. Let me open the SVM. Give me a second. Okay, here we go. SVM. Remember in SVM the part where for more than 2 classes. Remember it? Here I had a hello. Can you guys hear me?
Yeah.
Yep.
Oh, okay.
Yes.
What happened? The Zoom window suddenly just jump out. Zoom is not that stable, I feel. Anyway, that's the reason why they say this kind of some issue, something. Okay, it comes back now. Okay. Oh, you have a new clothes. Great. Okay, so here in, for example, 1 against all method. Remember here, I think I wrote something here. Okay. Attentive readers may compare this one with that one and argue that there should be an absolute value. Remember this part? And remember how I explained it? That is because if you substitute the number inside, you're going to see that this W1 equal to negative W2, and the W10 equals to negative W20. And that's the reason why we don't need a negative 1. It's not like 2 classes. 2 classes you do need, actually, also you don't really need, but you can make it a negative because 2 classes, negative simply means what? The direction. You see what I mean? However, here in lecture 10, 9, it's the same thing as multiple classes. See the point? I don't have to really care how many classes. I never said that you have only 2 outputs. I can have 200 outputs if I want, right? Okay, then the question is, as Arap just mentioned, hey, your, FKX, f hat kx could be what? Could be negative. Then why you mention that it must be the argmax instead of argmax absolute value, right? Okay, let's prove it. This proves I have to be honest that in this proof I'm a bit lazy because I avoided a critical proof of one formulation because that formulation, oh my god, you need to write very long. I did it on my paper. I didn't do it on the latex, and I'm kind of like lazy to really input it, and you're welcome to do it by yourself. And the proof is right here. So first of all, we assume that this inverse exists. Okay, in other words, we assume that X is a full rank. Okay, now this is the thing that I just mentioned, which is very, very important. We can prove this. Amazing. It doesn't matter what is your X. As soon, finally, it's going to be in this way. The first element is going to be 0, 1, and all other elements are going to be 0. Believe it? And it's true. And for the proof, you need to use the basic things of linear algebra and where's my mouse? Come on. And I need my mouse. And also, you need to make it clear about the meaning of xt inverse, and then make it to be xt. And then by playing some tricks, for example, write it to be the summation of the columns of the axis, make the column operations. And then finally, gonna show this one. Okay, so here, to make my life easier, I'm not gonna directly prove it. Instead, wait, actually, let me think about it. Maybe using this way. No. Using this way, you're gonna still have a sigma of the matrix and then inverse. It's still not that easy. So okay, let me save my life and directly use the MATLAB to show you a numerical example. Makes it really easy. Okay, let's suppose X is a random matrix of, let's say, for example, let's say 10 columns, let's say 4 rows. Okay, now wait, X equal to this. Okay, then let's calculate what's going to happen for this. So let's calculate x prime times x inverse, and then times x prime, and times ones of how many rows do I have? I have 10 rows, one column. Huh? Oh, wait, something wrong? How come?
Like not one in first column.
Yeah, it should be. Wait. There's something wrong. Did I make any stupid mistakes? Once 10 by 1, right? Let me see. Wait. Because I played it before. What happened? XTX times 1. Wait. There's something interesting, I think. Let me see, where is the mistake? Times x prime, inverse of this. Let me see that. 1, 2, 3, 4. Can you find any mistakes? That's really interesting. Let me play another one. How could it be possible? Did I make any stupid mistakes? Inverse of x prime times x prime times 1. Okay, let me see. Did I make any stupid mistakes? This is correct. Then why? M by 1.
What is your expected dimension?
The dimension is correct. The dimension for x is 10 by 4.
No, for outcome. For
outcome is correct. Outcome should be 4 by 1.
Okay.
Dimensions are no problem. Let me see. That's interesting. That's a very, very interesting thing that I don't know why it's not correct. It should be correct. Let me see. If I have. Let me see. Give me a second here. Fx. I think I need to consider it later after the class. There might be something wrong here, but the question is, if I don't have this one there, I can also do 58 because 58 is the key. 58 tells you that for any x, the summation of your estimated x must be 1. Estimated of the function fkx must be 1. So this gives you a very, very strong hint in the following. Let me see. If that's the case, because your b equal to this, right? So you have this times xty, and the times xty, if you have the y is in categorical in this way, and so you must have the summation of the yk, which is correct. And then you times an x, and that's interesting. It should be correct. Nothing wrong here. Let me see. Well, the reason for this step, the reasons are not that clear for me. Oh, okay, I get the point. I know the reason. Can anybody tell me the reason? What is the mistake that I made here? Yes, I got it. Remember, guys, x is not really random. Why? Because the first column of x must be all ones. Here you go. And that's also the key why this one correct. because finally when you operate it, you're gonna see everything else is canceled, but only the very first element will be left here, and that's where this 1 is from. This 1 is from 1 times 1. And okay, let's regenerate x. So in this time, let's do this. First of all, let me have a y for let me have an x-axis for fun. So x-axis equal to, for example, random, for example, 4 by 10, 10 by 4. Okay, now I'm gonna have x equals to, I have a 1's first, 10 by 1, and then put an x-axis here. In other words, what I'm gonna do is that I'm gonna add a 1, 1, 1 here. Okay, so let's have a look. See it? Now x equal to, a 1, 1, 1, this is a matrix plus this one. Now for this x, let's play it. I'll guarantee you it is correct. And then times 1's 10 by 1. Here we go. See it? Okay. And this is an example. Really scared me. Anyway, this is of course an example. As an exercise after the class, please try to prove this 57 by yourself. Okay. And don't make the mistake that I made. I even wrote it here, and I made the same mistake by myself. Great. X is the first element of X must be 1. Okay. In other words, your X matrix, the first column is 1. Okay. And in the MATLAB, the example that I just ran, I just randomly generate one, the second part, which is a random of 10 columns, 10 rows, 4 columns. Okay. And now let's have a look. So if X is in this way, then what you're gonna have? Because look at your fx. Your fx equals to what? Your fx equals to xt beta hat, right? Your beta hat equal to this. Okay, so the summation of your fkx equals to what? Think about this. So the summation here is actually for what? Is actually for the different y part. You see it? Because x is fixed. All x's are fixed, but the y part are different. So your summation of fx here is actually a summation of here. Get the point here? Because for different y's, and don't forget that y's, what is the structure of y's? For all y's are binary variables, right? For each row of the y, there must be 1, 1, and all others 0. For each row of the y, matrix y. Why? Because y's are category are category responses, right? So for each row, meaning that for each data, you must have one label, one category. That's the reason why for each row of y, there must be 1, 1, and all others are 0. Okay, so this one equals to this, the sigma of y. And as we mentioned that the y's are category, the sigma of y's are gonna be what? These y's are the column y's, okay? You know what I mean? Okay, let me write it down a bit more clear here. My y's are in this way. Y equals to matrix y equals to y1 dots ym, because I have total m categories, okay? This is, of course, what is dimension of me? This is in, come on, I forgot, it's not latex. N by M. Okay, this is your Y matrix. And then, remember, for each row of the Y is what? Each row of the Y means the multiple output for each data, right? And that's the reason why for each row of the Y, you must be what? You must be 1. In other words, what I'm talking is this. I must have y times 1 equals to 1. All these are vectors. Okay? This one is actually 1m. This is also 1m. Get the point here? This means that the summation of each row must be 1. Okay? So that if that the case, this summation of y means what? This summation of y becomes 1, 1, 1, a 1 matrix. See it? And because we have already seen that, we've already know that this one is this, right? So this tells you that this part is what? Is this part. And then x times this part becomes what? Sorry, there's a t, there's a typo. This should be xt. Let me see whether I can directly correct it here. Let me open my latex here. lecture 9. Let me see lecture 9. But in this case, I need to close this one. Otherwise, it's not going to be running. Clear all. Lecture 9. Where is my lecture 9? Open it. No. One second. Let me code it. Okay, here we go. So this is lecture 9. Lecture 9 again, and then what I'm talking about is here. Let me here's xt. Here's xt. And then I should have another xt, which is here, bt. Okay, here we go. Okay, that's corrected. Okay, so it's going to be xt here. And then it's going to be 1. Why? Because your x is in this way. Your xt is in this way, actually. Okay, so if that is the case, you have the first element is 1, and this is also 1, and it becomes 1. And all other x1 to xp, they're actually zeros, because you're going to times 0. So it doesn't matter what are the values of them. Finally, the conclusion is 1. So this shows you a super important property, that it doesn't matter what your x is. It tells you that the summation of your estimated function, the sum of them must be 1. Nice. Then immediately we can have an intuitive thinking or an intuitive argument of this method by this way. Because the expectation of the yk given x equals to x equal to the probability that the yk equal to 1. Why? Because your yk has only 2 values, 0 or 1, right? Regarding the expectation equal to what? Equals the value of y times the corresponding probability, right? If y equal to 0, you don't care what is the probability of it, because it's gonna be 0. So this equal to 1 times the probability that y equal to 1 given x equal to x, plus 0 times the probability that y equal to 0 given x equal to x, and finally equal to probability that yk equal to 1 given x equal to x. See it? And this means what? This means the probability that the category is really k. Okay, so people may say, hey, here we go. That's the reason why I want to make this. In other words, the expectation is going to be bigger if the chance is bigger. And hence, what we're doing here is actually to choose the largest probability, likelihood. This looks to be a good answer, right? However, you know what? There's a big problem. Why? Because although we have seen that the summation of these estimations equal to 1, but there's no guarantee that they are positive. They can be negative. For example, one value can be 2. The other value can be negative 1.1, for example. And the third value can be, for example, 0. What is the value should be? The third value could be 0.1. So the summation of these 3 equal to 1, right? Then this interpretation is wrong. Becomes, I cannot say wrong, becomes not strict, let's say, not proper. Why? Because the probability cannot be 2, cannot be negative 1. The probabilities must be between 0 and 1, right? However, you cannot force this number to be 0 and 1. There's no guarantee. The truth is that yes, this number could be negative 2, could be positive 10, whatever it can be. It just gives you the constraint that the summation of the estimation must be 1 of the outputs for one data. So is there a better way to really strictly define it, to defend it, let's say, defend this decision rule? And yes, there's a very strong and a very, very proper way. And here we go. So let's consider this. Let IK be the case column of the identity matrix. Okay, so you know what is IK? IK is everything 0 except for the case vector, the case element. Okay, IK is a vector. Okay, vector. Okay, now let me ask you: do you agree that we make the decision in this way? In other words, okay, suppose you have different f, f1 to fn, right? Your f case. I'm gonna see it's closest to which one, to which IK. And then I'm gonna predict the label to that way. What I'm saying is in this way. Okay, let's consider an example to make the life easier. Where's my word?
So it's same as the arc marks of.
No, it's different. It's different. So I had to be careful. Currently, it's different. Although finally, my purpose is to prove that they are the same. But currently, you cannot claim they're the same. Let me see. Give me a second. Let me. How to have a look at one screen just. Okay. So where are we? We're here. No. Let me see. Give me a second. View exercise. No, still. How to make it just one page? Let's see. Two windows. One by one. Okay, here we go. So what I'm talking about here is in this way. Let me open a new one. Suppose I have. Let's place a number for fun. For example, come on. No, I cannot. Suppose this number is, for example, 0. Okay, 0.2. Okay, the second number is, for example, 1.5, and the third number is 0.5, negative 0.5. And which one would you predict? What I'm talking about is this. I want to use this one. So what I'm going to consider is I'm going to consider it in this way. Norm. I'm going to use this one versus different IKs, and to see which one is the smallest. Okay, what does it mean? So for example, let's have a look. Let's have a look at, for example, this one minus, let's say, give me a matrix. I need a B matrix here. No, I need a B matrix. Okay, so suppose, let's talk about 1, 0, 0. Okay, so what is this? This is simply asking what is the distance of this prediction versus 1, 0, 0, right? Because perfectly, suppose the category is really 1, so I should have this perfect 1, 0, 0, right? And we're gonna calculate it, and actually I don't know what is the answer. Whatever the answer is. So this is gonna be kind of like let's make it a square, make my life easier. So this is gonna be 0.8 square plus 1.5 square plus 0.5 square. Who cares what it is? Okay. And then let's have a look at the second thing. That I'm gonna compare this one with 0, 1, 0. And what's gonna be this value? This is clearly smaller. And then it's gonna be 0.5 and 0.5 square. You can clearly see this one smaller than this one. And then the third case, I'm gonna compare this one with 0, 0, 1. And then this gives me a 0.2, and then this is 1.5 square, and the final is 0.5 square. And very clear, we're gonna choose this one. See it? I even don't need to calculate. I know this one must be the minimum. Why? Because this one is bigger than this one, is smaller than this one in terms of this item, and this one is smaller than this one in terms of both this and this items. So I'm gonna choose the second one. Is it clear? This way, yes.
Can we say before finding the minimum, based on the matrix that we have, f hat x, we can say that the class is the second one because 1.5.
Yes, that's the thing I want to prove. You're absolutely correct, Said. Congratulations, you have a very good math feeling. Yes, this is exactly 56. The way that you just mentioned is 56. You see it?
Yeah.
I'm gonna get the maximum one value. It's 56. And I want to prove that 56 is equivalent to 59. Because 59 is the way that we can accept. Why? Because suppose it's a perfect prediction, which means you have 100% accuracy. Then what's going to happen? You should have your fx equal to, suppose you are going to predict the label to, for example, k star, right? So you should have your fx hat to be ik star. You know what I mean? So for example, suppose it's a perfect prediction, then you should have what? If, let's say, fx is perfect. Let's say perfectly predicts predicts the label of x to be 2. The second label, okay? Then we should have what? We should have this one equal to I2, right? Equal to I2 equals to 0, 1, 0. So if it's perfect, then we should be this one, right? And of course, if it's a perfect to predict to be label 1, we should be 1, 0, 0. If it's perfect to be label 3, then we should be 0, 0, 1, right? And this tells you this formulation, this one, actually is what? Is asking, hey, so which one is the closest perfect selection for my F? You got a point? And that's the reason why this one is very persuasive. And people can agree with this. And whichever the K I can find, which means the Fx hat as closest to which perfect selection, I'm going to choose this one. Minimal, okay, this is argument, not argmax, okay? Now I'm going to show that this one is exactly the same as this one, which is argmax. And again, there's no absolute value. Why? Okay, let's see. So first of all, let's calculate what is F hat K to be. And here, you know, to make it a square, you know, to save my life. Otherwise, I need to have a square root. Okay, so have a look at Fx minus Ik. What is that going to be? So for all items, let's say FL not equal to this K, we're going to have what? We're going to have, let me make it big. That's here, okay. For all the L not equal to K, we're going to have F hat Lx itself and a square because I have the square root here, right? And for the kth column row, for the kth row, what do I have? The kth row, the Ik is going to be what? Going to be 1, right? So I'm going to have F hat Kx minus 1 square. So this is the thing. This is the value of for any K. Okay, now let's have a look. Suppose K star is the solution to 59. So for any K in the category K from, because total I have M categories, and this K is not equal to K star. Let's calculate. Let's make this norm
So
minus
the first part doesn't have the first part doesn't have any K, so we just look at the second part.
What are you talking about?
Isn't it? I talked about this expansion. So the first part doesn't have any K, but the second part is K. So the second part is minimized. I mean, the whole value is minimized when the second part is minimized based on K.
Let me see.
Isn't it? Because the first part is fixed. It doesn't have any K.
No, Said, be careful. Be careful. You cannot argue in this way. You cannot. You are talking about to prove this one, right? You cannot argue in this way. Why? Because this L as this F hat X itself is a variable. So this part is a variable still. You cannot say because there's no K, so I just have a look at it here. You know what I mean? Because here is something. Let me see. Give me 1 second. Wait, let me think about it. Maybe you're correct. Let me think about it. For Fx equal to 1. The question is, if you use that one, that value, that way to estimate, how would you make it predict that this one is a maximum? Because if that case, this one would be the one which is closest to 1, rather than the maximum one. Closest to 1, you cannot say it's the maximum one, because what if actually, yes, actually, Said, you are correct. Actually, you can prove it. Why? Because the summation of them must be 1. So the one closest to 1 must be the, no, you cannot claim it. Because what if my Fx equal to 2 point something? Yes, it's still the maximum. It must be the maximum, closest to the 1. And Said, you are correct. You can definitely use this method to prove. And so that you're going to choose the minimum of this part, right? And to choose the minimum of this part, you can argue that this k must give you the maximum fk. However, you need to have many different algebraic discussions. You know why? Because you are going to discuss two cases that the maximum fk is greater than 1 or the maximum fk is less than or equal to 1, and then prove it. In my personal view, I feel this way is easier, because this way you're going to see everything's, you don't need to discuss the cases. Everything's super direct. So because k star is my minimum value, so that use any k not equal to k star, this one minus this one must be greater than or equal to 0, right? Because my k star is the solution to here. Okay, so you're gonna expand this using this one and substitute inside, and be careful that here you have a fk hat minus 1 item in k, and here you have an item in k star. Okay, and then you just substitute here, and then you're gonna get this equation, and this equation, and you just operate one time, because a squared minus b squared equal to what? Equal to a minus b times a plus b, right? So use this trick, you can easily find that from here I get this. So it's very clear, because this one must be greater than or equal to 0. So finally I have what? Finally I must have fk is less than or equal to fk star. In other words, the k star is the maximum of everything here should be with the hat. I forgot the hat again. Everything here should be with the hat. Hat. In other words, the k star should be the maximum of the fk hat. Okay, so after the class, you can operate it and expand the items by yourself, and you're gonna see. And in this way, we proved what? We proved that 59 is actually exactly the same as 56. And hence, this 56 is reasonable. Okay? And this also answered your question, why there's no absolute value, because I don't need absolute value. One main reason is because of this. The summation of them equal to 1. If you do not have the summation of them equal to 1, then yes, you're correct. You do need absolute value. But since I have this equation 58, so I don't need it, and I can still guarantee that this is correct. Okay, any questions about this part? No question? And for Abdullah, are you okay with this? Because you didn't attend the classes before.
I have still some more things to follow, actually.
Yeah. So read the slides by your not slides, the class notes by yourself. Okay. If you have any questions, feel free to contact me. Okay.
Yeah, sure.
Okay. So then let's go to the second part of the linear regression. So the second part about linear regression is actually the the best subset selection, BSS. So first of all, let's start with the motivation. Why do we need to consider it even? So from lecture 9, we've seen that the least square regression solution is this way. And we know a problem, for example, is because this is an inverse of a big matrix, it may be not that convenient. Lucky we can use Cholesky decomposition or use the QR decomposition to solve this part, or not really solve, let's say to resolve this part, which means relieve this problem. Okay. However, it still may have some problems, because first of all, the OLS solution, if you just use this equation to solve, you may have something that is very, very small. For example, consider this beta equal to this. And you see what? Beta 1 is 5.5, beta 3 is negative 10.9, but beta 2, 1, 2, 3, 4, 10 to the power of 4, negative 4. It's a very, very small number compared with these two, right? Intuitively, we may ask, hey, if that's the case, so can we kind of like ignore it? In other words, I don't want to predict it anymore. I just want to have beta 1 and beta 3. We just ignore it. Can we do it? And you may ask, so why you want to do it? The reason is because in many cases, especially like in pharmacy research or drug testing, this kind of things, if you want to consider one more parameter, one more feature, then you're going to cost money. You're going to put the, start the money for experiment in this chemical. And hence, we want to try to minimize the number of features. So we are asking what types of which beta J can be deleted. So very clear, if I have a beta j like this way, which is very, very small, small compared with the other beta j's, I may want to delete it. And hence, we may not really apply the full OLS solution. And clearly, if we have smaller x size, then the problem gonna be smaller. This is very clear because of the operations here, right? Okay, and so this is the very first motivation that if some solutions, the value, or I should say the absolute value is very small compared with other beta j's, then I may want to, ignore it, or let's say drop it. And the second motivation is that here we considered in all the setting up of lecture 9, we considered that n is greater than p plus 1. But what if my p is greater than n, or my p is greater than n? Where's the application in this kind of things such that one experiment may be very costly? So in this case, your p could be bigger than n. Again, have a look at this kind of pharmacy research or drug testing. To do one experiment, it's going to be very, very costly. However, I do need to consider many, many chemicals because, in the drug research, you may not clearly know exactly which chemical. So you want to consider a lot so that you will not really miss some important chemicals. Then there's a problem. What if your p's are large but your n's are small? That you have a large number of components, a large number of features to consider, but you only have money to do a relatively small size of experiments. What should you do? And this is also something about sparse matrix. It's a sparse regression, and this is called the shrinkage, the shrinkage technique, or let's say the shrinkage model. That I want to have a least square regression that shrinks the size of the feature space. And for this part, mostly in lecture 11, we're gonna discuss the lasso and the ridge regression. And so in this class, we're gonna discuss the 3 types of this kind of sparse regression. The first one is the best subset selection, and the second and third ones are ridge and the lasso regressions, okay? And strictly, the best subset, you cannot really claim it to be shrinkage. Usually we say shrinkage is something, for example, it's not really 0. I make it to be 0. That's kind of like I shrink the size of beta. And of course, if you shrink the size of beta, you must shrink the columns of x, of course. So, so what are the best subset lasso and the ridge regressions? So actually, all of them have some penalty, or let's say they limits the norm of beta as a constraint of this OLS problem. So this is a very original OLS problem, original least square problem. And this solution everybody knows, right? As we just showed before. Now I consider, based on this problem, that I have a norm. I have a norm of the beta. Let's say the norm is, let's say I use k norm. This is less than, no, I cannot use k. P norm, did I use p before already? I've already used it. Let me use the k, q. This one should be less than or equal to k. The difference between the best subset, ridge, and the lasso is that best subset is gonna use q equal to 0. So q equal to 0, best subset selection. Q equal to 1, it's going to be a lasso regression. Q equal to 2, it's going to be ridge regression. Okay, so here are the settings of the shrinkage of the sparse regression method. And in lecture, which is this lecture? Lecture 10. In lecture 10, we're gonna discuss the best subset selection. Okay, and then let's have a look. The best subset selection, as we just mentioned, it's gonna be in this case. Okay, still remember what is 0 norm? For a vector, 0 norm counts what? Counts the number of non-zero elements. Okay, so for example, suppose let's just randomly play something for fun. Okay, let's have a look at this one. 0, 1, 0. What is the 0 norm of this I2?
1.
Equal to 1. Very good. Because I only have one element to be non-zero? What if it's, for example, 1, 1, 0, that equals to 2, okay? Okay, very good. So now let's continue here. So to make my life easier, I define F to be the feature space, 0 to P, okay? So I totally have P minus 1 features in the beginning. And what I want to find is to find a subset of this F, which includes K elements. In some cases, you may see it is less than K, but in most cases, it is going to be K elements, such that this part is going to be minimized. In other words, what I try to solve is this. Suppose this S is given. In other words, suppose I already know which K columns of beta of X, or let's say K elements of beta to be selected. Suppose I've already known it. Then I'm gonna still calculate the OLS solution. So if I've already known this selection S subset, then this problem is exactly the same as the least square problem. See it? And correspondingly, my solution is gonna be this way. This is very, very simple. The question is, how do you know this S? Because if you want to write it this way, this means S is known. That I know that I'm gonna choose columns S1 to Sk. And hence, what I'm talking about is I know that my XS is going to be in this way. The columns are S1, S2, and Sk. And here, use the matrix form. I can write it as X times pi S, where pi S is a permutation matrix. Are you familiar with the permutation matrix? Mahbouba and Abdullah, both of you should have seen it. Said and Arab. Do you know what is permutation matrix? Permutation matrix is something to operate. Remember from matrix operations, the right up, wait, no, Arab, you must know it. Otherwise something's wrong. Go to lecture 1 or 2, class 770. I mentioned it. Sorry, no. Go to problem 4 of homework 1. Yeah, I can tell you which one. That is the permutation matrix operations. Yeah, if you don't believe it, open your homework 1 of 770. It's problem number 4, if I remember correctly. I asked you guys to operate the left matrix operation and the right matrix operation, and then you're gonna see some rows are removed, some rows are added, and some rows, all columns the same. You know, left operation means rows, right operation means columns. Some columns will be kind of like 2 times the column added to, for example, 2 times the second column added to the fourth column. Remember? These are the permutation matrix, okay? So matrix permutation, you multiply a matrix permutation matrix in the right-hand side, especially here, what I'm talking about is that I'm gonna remove columns other than S1 to Sk. You know what I mean? So this actually is what? This actually gives you this matrix. Actually, this operation is to delete other columns. Okay, so of course, if I've already known S, this is super simple and I'm done. The problem is, how do you know S? How would you find S? So suppose I want to put S to be a decision vector, a decision variable. Actually, I'm solving what? I'm solving a min-min problem. You know what I mean? Actually, what I'm trying to solve is this problem. I'm gonna solve the min of S, and then inside I'm gonna solve the min of beta. And here is gonna be what? It's gonna be norm of 1 minus beta, 1 minus xs beta norm 2 subject to what? Subject to beta f minus s equal to 0. Subject to this, you know what I mean? Of course, this is a vector, and all these are vectors. And S is a set. Actually, I'm solving this min-min problem because that's a min-min problem, so I can combine them to be one level, make this bi-level problem to be one level problem, and make it into be this way, and I'm done. Which is right here. So this S star means what is the solution of S, the argument of this, okay? So actually I'm solving this problem. And this problem is indeed not easy. Actually, it's difficult to be solved. Let me, come on. Okay, so I'm actually solving this problem, and then if I substitute this notation inside, I'm gonna have this. See it? So in this case, I don't have the beta anymore. I just have the s. And clearly, this is a very difficult problem. If I use a brutal enumeration method, it's going to give me p plus 1 choose k. Why? Because I originally have p plus 1 columns, and I want to choose k of them. So I'm going to choose k out of p plus 1. And when p plus 1 or k is large, it's going to kill you. You will not like the enumeration method. It exponentially increases. Okay, not to mention large size, even medium size, you're going to lose. Say p equal to 100, k equal to 50. And no way, to the end of the year, probably cannot get the answer. So then how to do it? One thing is that I can use the bigger method to formulate it to an MIQP. MIQP is a mixed integer linear, mixed integer quadratic program. Q is quadratic, not LP. And we're gonna formulate it in this way. So first of all, my objective function is still minimization of the norm of, the least square. But I do have some constraints here. So this tells you what? This tells you that if my yk is 0, because my yk is a binary decision variable, if my yk is 0, then my beta j, my yj is 0, then my beta j must be 0. Okay, and the summation of yj's are less than or equal to k. This tells me that I can choose at most k yj's to be 0. In other words, I can choose at most k yj's to be 1. In other words, all other yj's must be 0, and hence all other the corresponding beta j's are 0. Okay, so in this way, it's very easy to see that this MIQP formulation is equivalent to this best selection problem, best subset selection problem, BSS. Any questions so far? No? Okay. And then actually one paper I want to strongly recommend you. And I remember at that time, I asked Abdullah and Mahbouba, you guys to read many, many times. I assume, especially for Abdullah, you have read at least 20 times. I assume it. Okay, so this paper is by Bartimos, and I haven't met the second guy. The third guy, last year when I was in MIT, I also met him, Rahul, a very, very interesting guy. So it was published in 2016. Yes? Question? No? Okay. So I would highly recommend you, all of you, to read it. Okay, so in that paper, it showed more details how to handle this problem, and also it gave several different formulations, MIQP formulations to solve. However, there are some different opinions between that group and also, the group in Stanford. So Hastie and Tibershrani, two Tibershranis, Ryan and Robert Tibershrani, they proposed that the MIQP method proposed here and in Bartimos' paper may not, have may not have statistical property if the signal to noise, the SN ratio is very high. So there's a problem. In other words, if the data does not have a very high signal to ratio, in other words, this works well only if and only if the signal to noise ratio of the data X is very high. So this is a problem. And the details would be in these two papers, 1 and 2. And there are some different, different opinions are also listed here. You are very welcome to read it. And if I remember correctly, later Rahul and Bartimos, they started, I forgot which year, 2018 or 19. Recently, actually, they submitted another paper to kind of like have some different opinions. You're very welcome to read these papers, and they really give you some very, very excellent views of how to apply this. Okay, but here, what I want to mention is that even if this MIQP works, however, the problem is that this problem is an NP-hard problem. Arab, are you familiar with the definition of NP-hard problem?
Not too much.
Not too much. Okay. So anyway, NP-hard. Did I have a link here? Read 3. What is 3? Let me see. 3 is the Wikipedia. Let's open it. So NP-hard is a non-deterministic polynomial time hardness. And usually, if a problem is NP-hard, what we mean is that we do not have deterministic polynomial algorithm to solve it, unless P equals to NP. You know, PNP problem is one of the most important and famous problem in computation theory. If you can get it, then you're gonna get a Fields prize, you know, the highest prize in mathematics. However, most people, including myself, we believe that P is not equal to NP. So if a problem is classified to be an NP-hard problem, usually what we mean is that for a large size of the problem, we cannot efficiently solve it. So even if this MIQP problem does not have this issue, that it works well, statistically well, only if the SN ratio is very high. Even if this is true, then still we face serious problem in solving it, because if your n, the number of total if your p plus 1, the number of total columns are large, then no matter what, solving this one will cost you huge amounts of time. So in the following, I'm gonna introduce two methods: forward stepwise selection and backward stepwise selection. Okay, so first of all, have you heard forward selection and backward selection in statistics? Especially in any regression classes? No?
Yeah, I had.
You should have, right? Probably in Gangshen's class, right? In general linearized regression, he should have already introduced the forward and the backward selection, right?
No, I heard in a multivariate course.
Yeah, it doesn't matter, it doesn't matter. So sorry, you said what? He hadn't introduced the multivariate?
Sorry?
You said he has not, or he has?
No, different.
So he has not? He hasn't introduced the forward and the backward selection in multivariate regression? Of course, it's multivariate. Are we talking about multivariate regression or
No, I didn't took this course. I did not take this course, multivariate.
Okay. Anyway, okay, so
one variable by one variable.
Different people may have some different forward stepwise selections, including some very heuristic ways that I try to avoid. First of all, I have to admit that both forward stepwise and the backward stepwise, they are heuristic methods. Okay, I never claim that they are accurate solutions to best subset. Otherwise, you have proved P equals to NP because their operations are P, are polynomial. And then, so if that's the case, why people are still so interested in forward stepwise and the backward stepwise? And to be honest, in most applications, people are using forward or backward selection. Forward stepwise or backward stepwise selection instead of later we are going to introduce, let's say, lasso or ridge, because especially for people who let's say started their research career, let's say before 1990s, they may not be that familiar with ridge and especially lasso. Ridge because it was created a long time ago because of convex property, but for lasso it's relatively new. It was proposed by Robert Ciabastiani in 1996. It's a relatively new. So, however, the forward stepwise and the backward stepwise selections, they're very efficient. They're very fast, and in many cases, they do give you very good options. So, using the forward and backward, we have heuristic operation estimations for the best subset selection problem too. This problem. Let's have a look. Let me see. Today, due to the time limit, let me start with the backward selection first, because backward selection is easier. It basically takes advantage of the statistical property of the least square linear regression, which is in lecture 9, actually. Okay, here's the lecture 9. Let's go to section 1.2 and 1.3, where I introduced the statistical property of the linear regressions. Where it is? Lecture. Come on. Here's lecture 2, and the lecture. Sorry, here's section 2, 1.2, and here's section 1.3. So especially section 1.3 tells you that to test the hypothesis for a single beta j equal to 0. In other words, I'm asking, hey, whether this beta j is significant or not. If the hypothesis is not rejected, that means it's not significant, so that I can drop this j's beta, right? In other words, I can drop one column. Okay, so we can use the t-test, or if we know this sigma, or let's say when n is large, then t-test and a z-test are almost the same. So we can also use the z-test, and these are the confidence interval, right? And clearly, you know, because no matter t-test or z-test, they look like this way. I know, really ugly. Anyway, they look like this way, similar. And the rejection region is here, something like this. Rejection region. So an absolute value of the tj, the t-score or z-score, which is large, gonna tend to reject. In other words, if it's relatively small, then we're not gonna reject it. And in other words, it's really not significant, right? Okay, so because of this statistical property, indeed, we have the backward selection. That first, I test the tj or zj for all the beta j's, for j equal to 1 to p plus 1. Then I'm gonna drop the coefficient with the smallest absolute value of the tj, of the t-score or z-score. Why? Because they are the least significant ones. Okay, so I drop one and then continue, and then I do what? And then I fit the least square regression again. Be careful that after dropping one, you're gonna update one column. You're gonna update this x as well. Okay, the x gonna drop one column as well. And this Kasi, according to what we learned in lecture 9, this Kasi is the j's diagonal element of this matrix. And Arab, do you still remember why? Because you are the person who asked me this question in the last lecture. Okay, that's because of what? Because of the statistical property of the beta here. And that's the reason why for each beta, the variance is simply the diagonal matrix, because the diagonal element, because this is the covariance matrix. Okay, and so I'm gonna drop it one by one until what? Until I have k columns left. So this is the backward selection for single coefficient consideration. Now there's a problem that, as we just mentioned in lecture 9, in some cases, we may want to consider this kind of coefficients by group. In other words, either keep it or drop it simultaneously. Why? For example, consider categorical outputs, categorical variables. For categorical variables, for example, a gender, male or female, it's meaningless you just keep one gender. For example, you keep just a male, and you remove the gender, another gender variable to be female. It's meaningless, right? We're gonna either keep them together, in other words, gender as a factor, as a feature, or we're gonna remove them together. In other words, we're not gonna consider gender as a factor in our regression model, right? So in this case, as we mentioned in lecture 9, we're gonna what? We're gonna do the F test, and the details are here. You can just review it. And the settlement of the regression here is that first, you want to show one very important property that where? Oh no, it's in lecture 10, not lecture 9. Let me see. One very important property is here. Suppose in your F group, where it is? Let me see. Here we go. An important property here is that if the group includes only one column j, so we're talking about the groups, right? But what if I just have one column j? So theoretically, this F test should give you the same result as this T test or Z test, right? And the truth is yes. Then it can be proved that the F score equals to the square of the Z score by 21. This Z, not T, okay, Z. And this is a very interesting and important result. By using this result, what can we do? We can simply just use F instead of use this. Because using the Z or T statistics, we're gonna test the coefficients one by one. But it's gonna give us a problem if, as what we mentioned before, for example, categorical output, categorical features. But for F, I don't have to consider them one by one by one. I can consider them simultaneously for some groups. For example, let's give a very simple example. For example, consider in this way. Suppose I have, for example, beta 1, beta 2, I have beta 0 as well. Usually beta 0 will not be, dropped. And then let's make several more. Okay, so I have beta 1, beta 2. Let's say beta 3, beta 4. Okay, enough. So what I can do is that I can group them in this way. Where is it? I can group them in this way. For example, I group them as beta 0 to be one group, beta 2 and 1 and 2 to be one group, and then beta 3 to be one group, beta 4 to be one group. Since here, it can be showed that the F test for one group is equivalent to the Z test. So I can use just the F test instead of the Z test, which is more generalized. And then what I'm gonna do is that I'm gonna do all this for the F test, and then again, I'm gonna drop the group. Be careful, I'm saying the group, not the efficient, but not the coefficient. The group which has the smallest F score. Okay, because for F distribution, it's similar. For F test, you're gonna have something like this way. And your decision, your rejection region is going to be something like this. So that for F test, if your F score is small, that means you're not going to reject it. That means this group is not significant. Okay. I said group, for example, suppose this group has the smallest F score. That means you're going to simultaneously drop beta 1 and the beta 2. You know what I mean? And then after exactly the same, you're going to repeat it. Okay, after drop this group, for example, then you have beta 0, beta 3, beta 4, and then do the OLS, the ordinary least square regression. Then get a score, get a result. After the result, you're going to see whether sorry, I forgot one logic here. After dropping them, you're going to count totally how many columns do you have. Here you have 3 columns, and then you're going to compare the columns left with K. If it is less than or equal to K, you're done. If it's not, you're going to continue it, which means you're going to solve the OLS solution for beta 0, beta 3, beta 4. And correspondingly, do not forget to delete the columns in X, okay? And then do the regression, and then do the F test again. And then keep dropping it. Suppose your K equals to 2, so you need to drop for one more time to see which one is the least significant until you finally have at most K variables, and you stop. Got a point here? So this is the backward regression. And actually, we already informally introduced it in lecture 9, and especially in lecture 6, I think, lecture 6. Logistic regression here. No, not this one. This is one of my reference. Where's my logistic regression? Let me see. And this South Africa heart disease. This is exactly the method that we're using. See here. In the beginning, I have so many columns. I have so many betas. And then we removed several, which, for example, I think we removed this. Why? Because their Z-score is less than or equal to 1, let's say less than or equal to 2. I mean, absolute value. This means they're out of the 95% confidence interval. So we remove it. And also we removed this one. If we use what? If we use the backward selection, what we're going to do is what? What we're going to do is that we're going to remove this one first. Why? Because this one is the least significant. And then remove the alcohol. I'm going to do what? I'm going to do the regression again. And then keep removing until the number of features left is less than or equal to k, and then I'm gonna stop. See it? Okay, so this is actually the backward selection. Any questions for the backward selection? Yes.
No question.
No question. Okay. So okay. Due to the time limit, let's stop our class here. And in the next class, we're gonna introduce the forward stepwise selection. Okay. That's everything. Thank you very much. Okay, let me be back. Thank you very much. And if you have any questions, please feel free to contact me. And that's everything about today's class. Have a good evening. Bye-bye.
Yeah, thank you. Bye.
Thank you.